Eighth grade. Today we're going to be talking about identifying and writing something called direct variation. And direct variation is kind of a sciencey term. You'll hear it a lot in like science papers, science journals. But it's very important to know the mathematical concept behind it before we really go forward. So I want to start by looking at just what direct variation is. So we're going to pretend that I have a lemonade stand. And at my lemonade stand, I am making pitchers of lemonade. And I need 5 lemons per pitcher of lemonade. I personally prefer my lemonade stronger than this, a lot more lemons, but you know, for the sake of the problem, we're going to do 5 lemons per pitcher. And what I'm going to do is, if I want to figure out what this looks like on a graph, for example, I would want to make a table, and we're going to have pitchers and lemons. So if I have 1 pitcher, well, that means I need 5 lemons. 2 pitchers would need 10. 3 would need 15, and so on. So if I'm trying to figure out an equation of this, it should be fairly simple to see what it is. That's going to be that my pitchers, P, pitchers times 5, is going to equal the number of lemons that I need. So if I take my pitchers, I multiply by 5, that's going to be the number of lemons. So P times 5 equals L. That's kind of fun. And if we look at this coefficient here, so the number next to P, my coefficient, again, is going to be the number next to my variable. So that would be the 5. If I look at that coefficient, so my coefficient is the same as the ratio. Looking back at the original problem, I did say 5 lemons per pitcher, which means I had a ratio of 5 lemons to 1 pitcher. And the coefficient in this problem is going to be the same as the ratio in the wording of the problem. And that's something that's always true about direct variation. So what I want to make sure that we define real quick before we go any further is having a real solid definition of direct variation. I'm going to write that right here. What direct variation is going to be any times one variable is a multiple of another. What that also means is we can always write this as y equals kx, where k is a coefficient. And that's going to be very, very important. So if it's direct variation, we'll just write it as y equals kx, where k is some coefficient. Looking back up to our first problem, where we had p times 5 equals L, we could write that. I'm going to write that in yellow because that was the problem color for the problem we used, as L equals 5k. So we have our 2 variables here and 1 coefficient there, just like my formula there tells me we should have. So that's kind of a generic formula for it, but the important thing is to be able to tell whether or not something is a direct variation. So looking at some example problems, the idea is to see if we can write it just like our formula here. So an example would be y plus 8x equals 0. If we look at this, we end up getting that y equals negative 8x because we can subtract 8x from both sides. And y equals negative 8x, negative 8 would be our coefficient, and this would be, yes, direct variation. Something that is a little less pretty would be, for example, xy equals 6. The general way to see if it is to just solve for y, so that's what I'm going to do. X is next to y right now. It is multiplying, so I'm going to divide by x to get rid of it. X divided by x cancels out, so I have y equals 6 divided by x. And looking at this problem right here, 6 divided by x is very different from 6 times x, so this is no, not direct. if we have something that looks like y, or x plus y plus 3 equals 0, then when I solve for y, I'll subtract x first. Y plus 3 equals negative x, subtract 3. I have y equals negative x minus 3. And looking at this, I do not have anything multiplying x, but I do have something adding on. And that right there means no, it is not direct variation. So direct variation is any time it follows our formula, which again is y equals kx. So what we want is y equals kx. Moving forward a little bit, if we are given a point and told that it's direct variation, what's really nice is that we can figure out what the equation is with only one point. So I'm going to do that right here, and we're going to say that we have the point 2, 12, and that's one of our points. And we know that this has to follow y equals kx. So if you're ever given a point and told specifically that it's direct variation, what you can do is plug in 12 for y and 2 for x. So I would get 12 equals k times 2. Then I just solve for k, and dividing both sides by 2, I would get that 6 equals k. So if 6 is k, I can write my whole equation as y equals 6 times x. And that would be how I can write an equation from just one point, knowing that it's direct variation. The nice thing about graphing direct variation, so if we're trying to graph it, I'll do this in yet another color, is that for direct variation, we always know that 0, 0 is always a point. So if we have the point 0, 0, all we have to do is find one more point and draw a line between them. So on my graph, if I'm given one point, say right here, then the line is going to be the line that goes through this point and the origin, and I can just draw a straight line through that. So graphing direct variation is also extremely easy. And that's pretty much the whole lesson today. What we covered was what direct variation is. We covered how to tell if something is direct variation. And on top of that, we also covered solving for a direct variation formula. And just like that, we're all done with this lesson. If you have any questions, please bring them to class. Make sure that you do the lesson practice at the end of taking notes for this video. I will see y'all in class.